Hi everyone. We saw several examples of acid-base reactions in the previous video, and here I want to identify the reactants as either conjugate acids or conjugate bases. Then we will use the concentration of hydronium to solve for what's called a pH value, which basically tells you how acidic or basic a solution is. Okay, let's see. Part A, conjugate acids and base pairs. Let's take a strong acid, nitric acid, HNO3. We'll put the phases, aqueous. We put that into water, liquid, and we get full dissociation into H3O plus, oh that's aqueous, plus the anion, NO3 minus. And maybe I should not say 100% dissociation, but very close. So let me put here, where am I going to put it? I'll put it right here. Around 100% dissociation. Okay. We know that HNO3 is the acid, and H2O is the base, the proton acceptor. But what about your products? Your products are going to be the conjugates. So let's start with the acid. The acid will lose its proton and become what's called the conjugate base. And for the base, I stopped way too early. That's not the conjugate base. Gotta keep going. My bad. HNO3 loses its proton and becomes NO3 minus. That's the conjugate base. Do you know what tipped me off? If that's not a base, so it can't be the conjugate base, because going in the opposite direction, it's losing its hydrogen, its proton, sorry, to make water, so it's acidic. Okay, so that's a good clue. This base will gain a proton and become what's called the conjugate acid. It literally is acidic. It will act like an acid to get back to the other side. Those are your conjugates. Why don't we look at a weak, not a weak acid, but an acid-base reaction where water is not the base. We haven't seen this before, actually. Let's take NH3 gas plus HCl gas. Right, so there's no water. HCl gas. The water's not going to be a reactant, but it will facilitate the reaction. So we'll dissolve everything in water, and we get NH4 plus Cl minus, and both of these are aqueous. You might wonder, why do they put a full arrow? Because HCl is a strong acid. So even though we're not using water, it will fully dissociate and you will make these two products. And we identify the acid and the base. That is our first job. That's the acid. Right? It gave up its proton to ammonia, which is the base. So where is the conjugate base? The acid turns into the conjugate base once it loses its proton. Here's the conjugate base. and your conjugate acid came from the base. Conjugate acid. Okay, let's practice. A problem that you may see on an exam or the textbook is something like this. You're given a pair. You know, our title is conjugate acid-base pairs. Okay, you're given a pair of molecules. Let's do H2CO3 and HCO3 minus H2PO4 and H3PO4. Oh, that should be a minus. The first one. Let's take the same molecule, H2PO4 minus, and now let us have HPO4 2 minus. So what's going on here? The directions may say label the first compound as acid or base and label the second compound as its conjugate acid or base. So over here, they're asking you acid or base. And for this column, is it the conjugate base or conjugate acid? I'll do the first one. We have H2CO3, and it looks like to get to the other side, we have to lose a proton. Therefore, what loses protons? Acid. So this is an acid conjugate base pairing. Can you do the other two? Okay. What about these two? This one accepted a proton. So we have a base conjugate acid pair. And we can always double check. We call this a conjugate acid. Well, to get back to the original, does it have to lose a proton or accept a proton? It has to lose a proton, so it acts like the acid. This one, we have now not a base because it loses a proton. It donates a proton. So we start out with the acid, and we create the conjugate base, and that's the pairing. Okay? That is conjugate acids and conjugate base pairs. Let me talk now about what's called the pH scale. Some of you have heard of it before. pH scale really is a scale of how acidic, but also how basic a solution is. Usually the range is 0 to 14. Usually the range. Okay, but we could be outside of that range for extreme cases. Let me draw the scale, 0 to 14. Let's start with 7 actually. 7 you've heard possibly that it's neutral pH. So 7 is neutral. Now I won't go into detail exactly what that means, but also this is at 25 degrees C. When you change the temperature, actually the value of a neutral pH changes. Again, we'll get into those details a little bit later in future videos. Okay, if we go in the right direction, we're going to be more basic. So this is blood, a little bit higher, 7.45. And then, what else? I have some other examples. Baking soda. Baking soda is 9. Remember baking soda? NaHCO3. And then we have bleach. Well, here's soap. soap is 12, pretty high. And then 1 pH unit above that is bleach, 13. Okay, that's pretty high also. Let's go in the other direction. I only have actually 2 examples. I have wine, pH 4, and then stomach acid. That's a pH of 1. Okay, in your stomach right now, the pH is 1, pretty acidic. So again, this is getting more acidic as you go in this direction. And your solution is getting more basic as you go in this direction. Okay, a couple things about the pH scale. You can have a number that is negative, so you rarely see it, but you can have negative pHs. And you could have pHs that are higher than 14. But this is the normal scale, 0 to 14. The next thing is the pH depends on the strength of the acid or base and also the concentration. And we're going to do some calculations next. Depends on strength. We won't talk about actually the strength until a future video, but we are going to do calculations to get pH based on concentration. It depends on strength of acid or base and concentration. Okay. In part C, let's do those calculations. pH is a log scale, and H actually you could think of comes from proton, H+. So we're going to convert these concentrations of H+ into a log scale called the pH scale. And I'm just going to label this section calculation of pH. But this is of strong acids. Weak acids are a little bit trickier, and we'll get to that in a future video. Let's do the strong acids though right now. The equation is this. One of them is pH equals negative log of the concentration of H+. You know that the square brackets means concentration. That, if you're in water, and almost all cases you will have this reaction in water, that's the same as pH equals negative log of the hydronium concentration. And that's the one I'm going to put in a box. And we know that because in aqueous solutions, every H+ that is created will bond to H2O to make hydronium. Okay. Let us take an example of a strong acid. Let's do HClO3 plus water goes to H3O plus ClO3 minus. Okay, you should be able to identify the acid, the base, the conjugate acid, and the conjugate base. But I won't do that here. You know how to do that. Now, again, I'm going to emphasize we get around 100% dissociation. Very, very close. Okay. What that means is that if you dissolve, let's pick a random number, 0.00050 moles of HClO3. Because we get 100% or near 100% dissociation, we're going to have the same amount of H3O+. So let me do this in 1 liter water. It means that if a strong acid, okay, so we got to understand that this is a strong acid, that the concentration will be equal. So it means you have 0.00050 moles of H3O+. So you're going to plug that number in. Oh, not that number. You have to get the molarity. But because we're in 1 liter, this is 0.00050 molar H3O+. Okay. Let's do the calculation. Just give me 1 second. 1, 2, 3, 4. It's -4. Let's do the calculation. pH equals negative log of 0.00050 molar. That equals. The purpose for the pH to describe the amount of H3O plus stems from the fact that these concentrations are going to have a very, very wide range. To get something into a more compressed range, we're going to take the log of the molarities. And I have set up an example in just a bit. But instead of dealing with this molarity to describe the H3O plus concentration, we would actually use the pH, which comes out to be, so we've got to take the negative of that, which happens to be 3.30. See, that is on the pH scale that we discussed, 3.30. Oh, by the way, pH, there are no units, so this is unitless. I call it if there's a difference of 3.3 going up to 4.3, I call that a 1 pH unit difference. But there is no actual units. Okay, let's take a look at a couple examples. Actually, we have 5 of them, just for practice. We have the concentration of H3O+, and we have pH. So go ahead and calculate the pH for these concentrations. They're going to be in increasing amounts, because I want to show you the range that the pH scale can cover, how wide a molarity range it can cover. Here's an interesting one. Concentration of 1, we're going to have to take the log of that, and then 2.55. So this is increasing. Concentration of H3O+. How acidic are we going to get? Go ahead and pause the video if you want and do these calculations. I have the answers already. Okay, the pH for the first one is 4.43, 3.08. Yep, pretty close to what we had for 5 times 10 to the minus 4 molarity. I'll just plug in my computer. Okay, next we have, less than 1, 0.44. Whoa, pH can also be 0 if the concentration is 1 molar. 1 molar, and then if you get above 1 molar, then you start to go negative. 2.55 is negative 0.41. Okay, that is figuring out the pH of strong acids like HClO3. Let me put a little note here. For weak acids, we're going to do that later. For pH of weak acids, that's a future video. it gets complicated because dissociation is not near 100%. Actually, it's closer to maybe 1% or 5%. So the problem is with weak acids is when we have a weak acid. Now, I'm going to use this example, HClO. See, remember, HClO3, chloric acid, and HClO4, perchloric acid are strong acids. But this is what? This is hypochlorous acid. This is a weak acid. And the problem is, when I dissolve it in water, I will get an equilibrium because it's not 100% of the products. But even more challenging is that this concentration is not the same as this concentration. So we got to figure out first the molarity of this. Even if you're given, right, even if you're given this molarity, we don't know that molarity. They are not equal. That will be in a future video. Okay, the last thing I want to go over in this video is going in the opposite direction to calculate for H3O+. This is part D. This will be fast. Calculate. Oh, I forgot. The title says we also want to calculate pOH. No problem. pOH and the concentration of H3O+. pOH is simple. I'm not going to derive it, but let me give you the equation. pH plus pOH equals 14. Okay, you can put it in a box. But there's a caveat. There's a warning here. It has to be at 25 degrees C. Just like the neutral pH of 7 is only true at 25 degrees C, this is only true at 25 degrees C. So therefore, we had a pH equal to, what was it? 3.30. Oh no, let's use this one. 3.08. 3.08. Therefore, the pOH equals 14 minus 3.08, and that equals 10.92. Okay. I will derive this later, in a later video. I wanted to show it here because if you know pH, you should automatically know pOH. But I will derive this equation in future video. In a future video. So the next calculation is, how about this? If the pH equals 3.08, we know the pOH, but do we know the H plus concentration? What is the concentration of H plus, or if you're in water, H3O plus? So we're going to do some arithmetic. We know that pH equals negative log of the concentration of H3O plus. And what we do is we bring the negative sign over and we make those exponents or make those powers. So let me just bring this over, the negative first, make it a little bit easier. Oops. Let me do this in purple also. So if we do the 10 to the negative pH, that equals 10 to the log of H3O plus, and that will simplify into just H3O plus. The thing is, on my calculator, if I do this, 1 times 10, if I do 1 time, no, Maybe I should just show you the calculator. Because I want to plug in negative 3.08. So if I do 1e negative 3.08, which is what I normally do for raising to the power, I get an error. So for me, for my calculator, 1e negative 3.08. Where are we getting 3.08? That's the pH that we're using up here. Okay. So this equals 10 to the negative 3.08. But for my calculator, if I do that, that equals error. I have to do 10 caret negative 3.08. 10 caret negative 3.08. Okay, so that in scientific notation is 8.3 times 10 to the minus 4. Do not forget your units. This is a molarity. This is a concentration. And we could double check. We got 3.08 when we had a concentration of 8.4 times 10 to the minus 4. So there was some rounding error or rounding discrepancy. Here we have 8.3 times 10 to the minus 4. Okay, close enough. If we had more units or more digits, we would get a more accurate answer. So that is how you calculate the concentration of the H3O plus from the pH. What then do I need to square? Not square, but to put in a box. A little bit messy, but it's this one. Concentration of H3O plus equals 10 to the negative pH. Now, you may have that on your equation sheet, but you saw how if you don't do practice, you may run into problems on the exam. You got to practice and you got to know your calculator. This is for my calculator. This might work for your calculator, okay? But I have to switch over and use the caret and put 10 to the negative 3.08.